When you get into these shear force diagrams and bending moment diagrams like we're doing just now, what can happen is you kind of lose track of what you're talking about. So you get so interested in drawing pretty graphs that you're forgetting what they actually are, these graphs, or what they're trying to represent. And so let's just go back and remind ourselves what all these things are. And so I've got some bullet points here. I'm going to talk through those and just make a video summarizing where we're at. So right back to the start, shear is an internal force. So it's the force that carries, it's the internal force that carries an external force from one place to another. And the shear is quite hard to show if you've got a long thin element, but I can do it like that. And it's what shear tends to turn the squares or rectangles drawn on the element into diamonds or rhombuses or parallelograms or however you want to think of them. So that's a shear. It's a little bit hard to show with a thin element, but with a fat, wide element, it's a little bit easier. It won't be perfect because my fingers aren't exactly straight. You can see how those squares are going a little bit into parallelograms or diamonds. So that's a shear force. And so your shear force diagram is just a measure of how much that's happening. And so if it was just like this, it would be a low shear force in your shear force diagram. If it was like this, it would be a high shear force in your shear force diagram. And the whole reason for doing this is if the shear force gets too high, you'll get a shear failure. A shear failure looks something like that. Okay, how it actually forms depends on the material, but it would be something like that. Okay, so just to take that back a bit, what I also want to show you is just what it looks like in real things. And so to see shear, so what I've got here, let's just come out of there a minute. So what I've got here is I've got a universal column. That's what this element that's green at the moment, that's called a universal column. And so it's an I-beam is another way of talking about it, or an H-beam. These are usually referred to as H-beams because it looks like an H. They're used for columns in building steel structures. Now, the parts of that are, these top and bottom bits are called flanges, and the bit that joins them together in the middle is called a web. You don't have to remember that for this course, but it is a good thing to kind of get your head around, start learning these terms that you'll hear people on site or in the workshop using all the time. So you've got flanges and web. And what I've done is I've created a little beam like so, welded on some blocks, and I've actually supported it. You can't see it, but it's supported here and supported here. So those are like the supports we see in our diagrams. And I'm going to load it on top here. I've just put this block on top, so I've got something to load onto. To see shear, it's usually the case you don't really see shear if you've got a long beam that's not very deep. The time when you see shear is when you've got loads very close together and you've got a pretty deep beam. And then you'll start to see shear becoming critical. So it's more important than the bending effects that we'll talk about next. So what I've done in here is I've done an analysis. So I've stuck a load on top. And then what this program will do is it'll figure out what would happen to that beam under that loading. So I think this was like 20, you can probably see actually. 200,000 newtons, so 200 kilonewtons, 20 tons is what I'm applying onto there. Pretty big load. So if we now look at what happens to this beam, let's just take it to the actual. So if we apply, so this is a 300 deep beam, it's 300 millimeters deep. We're applying 20 tons, did I say? I think so. 200 kilonewtons, 20 tons. What are we going to do that for? And this is the actual deformation of that. And I'm just going to turn on the squares here. And so let me just come out of the stress analysis. And so that's, if you apply 20 tons to that beam, that's what would happen to it. You wouldn't really see a thing. And that's what I'm talking about rigid bodies. So it might look like nothing's happening. This seems like a rigid body, but actually it's deforming a little bit. And what we can get this program to do is we can get it to exaggerate it. And so what we'll do is we'll times it by, it's not really times by 5, but it's just sort of times it by 2. It's just exaggerating the deformations of the beam. It's multiplying them by a factor. And what the colours show, they show the stresses in the beam. And I'm not going to get into the ins and outs of that. You'll talk about stress a little bit in materials for those of you that are doing construction management, or if you're doing it any of the courses, you'll talk about stresses at some point. And so I'm talking about von Mises stress. Don't worry about what that means. In this case, it's really these green areas are showing us the shear stress, or they're high because of the shear stress. These little red areas, something different. Don't worry about those. Let me turn on my mesh. So if I look at it undeformed, so that's with no deformation at all. It's not showing any deformations. You can see I've got little rectangles here. There's a triangle in the middle. Ignore that. You've got little rectangles. But if I now exaggerate the deformations, you can see that those are turning into little parallelograms. So they're no longer got square corners. They're not at 90 degrees anymore. And that tells you that the shear is high through this area. As we come down through here, they actually, although they're deformed, they're not really forming these parallelograms. So the corners are almost square. So the shear through here would be a bit lower. And then the shear is getting higher again up through here. And that's really what your shear force diagram is telling you about. When shear is low, your shear force diagram will be near zero. When the shear is high, your shear force diagram will have a higher value. One other thing just to note for this one. So what you can see is for shear, most of the stress from shear is in this web. Remember the vertical one was called the web. And there's not much stress because of shear in these flanges. Okay, so the green color is the kind of higher stresses. Blue means there's no stress at all, or not much stress. And so you can see shear is carried by this web element. Now, let me go back again to Ladybird, if I can. This is just this document camera. And you can kind of see why that would be the case. So if I try and shear this way, it's dead easy. I can shear it no problem. But if I try and shear it this way, it gives a lot more resistance to shear in that direction. And that's why the web carries most of the shear in a beam. It's something we will get to in another course. For those of you that have another course with me, we'll get to a bit more about that. Okay, so that's the kind of basics of what shear is and what we're drawing when we're drawing a shear force diagram. So don't lose sight of that. Don't forget what you're actually drawing here. It's all about that shear deformation and how bad it is, or how big it is, the shear deformation. Close this one. Yeah. So let's go back to our list of things to think about. I'm just going to close. Hopefully that closes down. So we talked about that. If you draw squares on an element and shear it, the shear will tend to turn the squares into diamonds or rectangles into parallelograms. Shear force diagram, SFD, stands for shear force diagram, and is a way of representing the magnitude, we should probably say. Of course I can't spell, I'm an engineer. Magnitude of the internal, got it already, of the internal shear at all points along a beam. That's what we're trying to do here. Okay, so when you're actually solving these problems, let me just move this out of the way. When we're actually solving these problems, the first step is always to figure out the reactions. I've been over that enough times, I'm not going to do it again here, but you're just doing sum of Fy is 0, sum of the moments is 0 about either of the supports. Check your answer with the other support, and you'll find the reactions. Then we're going to look at this, all of the different rules we're using to draw the shear force diagram. Excuse me. So what are we doing? Well, when it's point loads, it's pretty easy. So this is going to be our shear force diagram. So drawing the axis there. And so then what we're going to do is we're going to start at the left and work to the right. Point load's dead easy. All you do is if you see a point load, you move the same distance in that direction. I've tried to do this to scale, I think. And so what I can do is just go up by the same number of squares. So it's just a little bit more than 3 squares up. We'll do it in red so you can see it. Just a bit more than 3 squares up. And then between forces, if it's all point loads, or even between line loads as well, anywhere where there's nothing happening on that beam, the shear force is just going to stay horizontal. If it gets to a force, it's then going to go, it's going to follow that force, magnitude and direction. And so this one is 3, is it? 3. So it's going to go 3 down. It's going to get somewhere near 0. Not quite 0, but somewhere near 0. And then keep going left to right. We're going to get along to the next. Nothing's going to happen, so it stays horizontal. Get to the next force. This time we're going to go 1 down. I think it's not quite drawn. It's not quite exactly in the right place, but I'll just draw on the squares. And so we're going to go 1 down, so we'd end up here. Then nothing's happening, so we just go horizontal till we get to the next force. And then we do the same magnitude down the way. So this was 2 squares. I'll draw on the squares, I might tidy that up later. And it's going down 2 squares. So we get to here. Then you keep going along until you got to the reaction force. Nothing in there, so it's horizontal. And then it just goes straight back up. And it comes back to 0. And I think that would be the case where there was a cantilever no matter what. And then you just colour in that diagram. So what are we saying here? Well, that distance is just equal to R1. So let's just write this out. What we can say is the change in shear is equal to R1. Here, the change in shear is equal to F1. And then in between, it's horizontal. Okay, and we can keep going through. Change in shear is equal to F2. And it's both the magnitude and the direction. Here, change in shear. Oops, I think I'm doing that upside down. No, it is delta. Change in shear is equal to F3. And the last one, the change in shear, magnitude and direction, is equal to R2. And then just shade it so people can see where it is easily. And then if there was numbers, you just write the numbers on the top here. In my case, it's going to get a bit messy doing that here. Okay, so pretty easy. Was there anything else I needed to say for point loads? Don't think so. Yep. And so just remember, if you wanted to check your answer, you could just take a section, use the method of sections to find a particular shear at a particular point, using either the left-hand side or the right-hand side, and just to check your answer. So that was for when there's just point loads. Then we've got some more rules for when there's both point loads and, I might have to move this stuff down a little bit. I might have to zoom out a little bit so you can see this. This one we've got line loads and point loads. So what are we doing this time? To draw the shear force diagram. It's going to come up for, I think it was exactly 4, this one. I'm just going to rub out that because I think it was exactly 4. 1, 2, 3, 4, so that should be okay. I did put my shear, what I didn't put on for my other axis, which is not good of me, was I should have said that this is the distance along the beam, x in meters. This is the same here. This is x in meters distance along the beam. And this is V in kilonewton. So shear, the letter for shear is V. Okay. So this time it starts the same. So the first thing we get to is this reaction. Am I going to have enough space? No, I am not. Let's make enough space. So the first thing that's going to happen is going to follow that R1 again. So it's going to go 4 up. 1, 2, 3, 4. Okay, so you would have had to find these reactions first using the normal methods. But once you've got them, it's pretty easy. So we go up by that reaction. Now I'm drawing horizontal, but I can't draw horizontal. All I know is it goes up to it and it starts from here. Now, I do have something here. I've got a line load, and there's a few ways you can think about it. One way you can think about it is that the total load along this distance is going to be W1 times L1. It's the area under that line load. And so by the time I get to here, I must have dropped by W1 times L1. We'll just count squares. So that would come down by 4. And so we'd come right back down to 0. And so we know by the end of that force, we're going to get to this point. So that's the first way we can think about it. And then you can just say, look, it's a diagonal line. So it's a straight line between those 2 points. A UDL, so uniformly distributed load, will always give you a straight line for the shear. Another way to think about it is this is just, if suppose this was kilonewtons and this was 1 kilonewton per meter. For every meter you go along, it's going to drop by 1 kilonewton. So it's going to drop, 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 drop 1 kilonewton each time. So let's start putting some of these things on. Let's try and think how I'm going to put them on. So let me just use a small red line for these. So what would happen between here and here? Just draw it as a little line like that. And delta V, so the change in shear is equal to, and it's magnitude and direction again, this is going downwards, so the shear is going downwards. Okay, so this magnitude, this line load is going downwards, so is the shear. And so delta V is just going to be equal to W1 times L1, the area under that line load. Or we can think about it, for every unit length you go along, in our case that's meters, if you go along 1 meter, you must go down W1 kilonewtons, because this is W1 kilonewtons per meter. So if that was 1 kilonewton per meter, for every meter long you have to go down by 1 kilonewton. Another way to think about it is for any distance along here, the amount you go down is just equal to the area under this. So as you come along 1, the area, in our case, is 1, if we're just counting squares. If this was like 10 kilonewtons, you'd come along 1, that would be 10, so 10 kilonewtons per meter. If that was 10 kilonewtons per meter, you come along 1, you go down the area under here, which would be 10 kilonewtons times 1, you'd come down 10 kilonewtons. If you go along to here, then you can just say, look, say this was 10 kilonewtons, then you'd have gone along 3 meters, so you'd have come down 30 kilonewtons. And so another way to think about it is just for any point in the shear force diagram, the amount you drop is just equal to the area for the equivalent distance along this UDL. So heaps of different ways. They're all really the same thing. And what it really comes down to is the gradient of this line is equal to the magnitude of this line load, allowing for its direction. And so the gradient of this line, for those of you that have done the maths, you just do change in y divided by x. It's going to be exactly the same as the magnitude of that line load. Okay, so lots of different ways to think about it. The one I usually use, well, this one's nice and easy. You just calculate the total area. It's got to drop by that force. So you just do W1 times the length. It's got to drop by that force and then just draw a straight line between them. But any of those ways works. Now, between here and here it is flat because there's no forces. Then it's just a point load. So we're just going to go magnitude and direction. It's 2 squares, whatever that represents in real life. Could be 2 kilonewtons, could be 20 kilonewtons, whatever. Oh, don't know why I'm drawing an arrow. So this, I need to just make this thicker. It's only the annotations I wanted to make thin. Coming along there, then it goes flat because there's nothing there. Then it goes down by F because it's hit a force. How would we annotate that? Well, delta V would just be equal to the force, allowing for its direction. Then between the force and the next line load, it's just going to go flat again. And then in this case, so we're just counting squares. This could be a value, you'd have to calculate the value. But look, we've got the area under this is 2 squares. So over that distance, it's got to go down by 2. Just think, looks like there is a mistake. Oh, no, we're still going down. I was just going to go back up there for a minute. but this is still pointing down the way, and so we're still going down the way. And the reason I realized I was making a mistake, because then I would have got back near zero, but it should be this that brings us back to zero. This reaction force should take us back to zero. But anyway, by the time we get across this, we should have gone down another 1 kilonewton, if W1 was 1 kilonewton, just in terms of counting squares. But this distance here is just, or this change in the shear is just going to be the area under this, and it's going to be a straight line between it. And I've done them thin again when I shouldn't have. Let's just draw this on. So for here, the change in shear, this is an annotation, so it should be thin. The change in shear there is just going to be equal to the magnitude of that line load times its length, and I haven't given it a length. So this should be L2, this should be L1. So it's going to be W2 times L2. And then there's a little bit of a gap until the next force, so it would go horizontal again. Get the right line thickness. And then it would go up 3 because that force is going up 3, and that would bring us back to 0, so we can be pretty confident we've got the right answer. And I think that's pretty much everything you need to know about shear force diagrams. So you're just remembering, so I was kind of counting squares here, but really what you're saying is if you've got a line load, then it's just going to go, whatever this magnitude is, it's going to go, if this is downwards, it's going to go downwards by that magnitude for every unit of length that you go along. So for every 1 meter you go along, you're going to go down by W1 kilonewtons. Or you can just calculate the total load under there, just times W1 times its length, and then the total drop over that whole distance is going to be W1 times L1, W1 times L1, and you can figure out where those 2 points are, and because it's a UDL, it'll be a straight line between them. And then horizontal if there's nothing, straight down or straight up, depends on the orientation, but this one's downwards, so straight down if you had a force, horizontal if there's nothing. Go down by, this one's half a square, but it might be, I don't know, if this was 10 kilonewtons, this might be 5 kilonewtons, so you'd be going down by 5 kilonewtons every unit length you go along. And then there's nothing, so it's horizontal. Then it hits a reaction force, so it goes back up. And then just to make it easy to see, you hatch it. So in general terms, that's all of the rules for drawing a shear force diagram. What we'll look at next is how you draw a bending moment diagram.